Welcome to our discussion on real population growth. So let's look at an example with varying growth rates. So the average annual growth rate for world population since 1650 has been about 0.7%. However, the annual rate has varied significantly. It peaked at about 2.1% during the 60s and is currently, as of 2017, about 1.1%. I believe in 2020 it's gone down even more. I think these last couple of years have seen some of our lowest growth rates in a long time. So let's find the approximate doubling time for each of these growth rates. Use each doubling time to predict world population in 2060 based on a 2017 population of 7.5 billion. Okay, so using the approximate doubling time formula, which we can use because all of these rates are small, right? We can only use the approximate formula for things that are 15% or lower. We can find the approximate doubling times for these three rates. So for 0.7%, it's going to take 100 years. For 2.1%, it's going to take 33 years. And for 1.1%, it's only going to take 64 years. So to predict the world population in 2060, we use the formula that the new value is going to be the initial value times 2 to the t over t double, right? So we set the initial value at 7.5 billion, and note that 2060 is 43 years past 2017, so that's going to be our t. And then for each of our three growth rates, we use our different years that we just calculated, 100, 33, and 64. So we can see that in 2060, based on what kind of average growth rate we have over that period, we could have anything between 10 billion and 18 billion, and those are two hugely different numbers, right? So overall growth rate, the world population growth rate is the difference between the birth rate and the death rate. So it's just basically growth rate equals birth rate minus death rate. So for any particular species in a given environment, the carrying capacity is the maximum sustainable population. That is the largest population the environment can support for extended periods of time. In 1950, the world birth rate was 37 births per 1,000 people, and the world death rate was 19 deaths per 1,000 people. By 75, the birth rate had fallen to 28, and the death rate had also fallen to 11. So we can contrast the overall growth rates for those two periods and see that in 1950, it was 1.8%. In 1975, it was 1.7%. So it actually gone down. So a logistic growth rate is experienced basically when you have a fractional growth rate close to the base growth rate R. So as the population approaches the carrying capacity, the logarithmic growth rate approaches 0. The fractional logistic growth rate at any particular time depends on the population at that time. So the carrying capacity and the growth rate R go into our formula, and we see that our logistic growth rate is going to equal R times 1 minus the population divided by the carrying capacity. I know that sounds like a lot of gibberish, but it's basically just whenever the population is small relative to the carrying capacity, we can use this. It's not really working now because our population is approaching its carrying capacity. So in the exponential case, the growth rate stays equal to R at all times. In the logistic case, the growth rate starts out fast, basically equal to the exponential. And as time progresses, the growth rate becomes even smaller because it needs to zero out as it gets to that carrying capacity. So you can see exponential just keeps growing no matter what, and it'll blow right through the carrying capacity, which will be a problem for, whatever you're talking about. I mean, even if it's something as simple as elk and caribou, if they outgrow their environment, i.e. they start outgrowing their food source, then what happens is they start dying off at huge rates because of the lack of food source. So that's why they'll, extend hunting seasons, or in the case of Yellowstone, they reintroduced wolves to Yellowstone to help cull the herd and keep them from growing so fast, things like that. Whereas the logistic growth rate grows fast in the beginning and then it levels off. This becomes a logistic curve, which is basically like a flattened off curve as it approaches the carrying capacity. So are we growing logistically? Well, the worldwide population growth rate has been slowing since about 1960 when it had its peak of 2.1%, and the population was about 3 billion. Now assume that these growth rate and population values represent one point in time on a logistic growth curve with a carrying capacity of 12 billion. That's just what scientists have estimated is the carrying capacity of the planet. Obviously, there's things that we could do that could make that bigger, and there are things that we could do that could make that smaller. So does this model successfully predict the 2017 growth rate of 1.1% given the 2017 population of 7.5 billion? Well, if we plug everything in, right, we begin by using the 1960 data to find the base growth rate R in a logistic model that uses the 1960 data values. You should confirm that solving the logistic growth rate formula for R gives us this, right? So basically all we did was we took this formula and solved for R, right? So you get R is going to equal this thing divided by this thing. And that's what we have here, growth rate divided by all this stuff. All right, so if we plug in what we know, we substitute in all the values that we know. So the growth rate in 1960 was 2.1%. The population in 1960 was 3 billion. The carrying capacity is 12 billion. If you do all this math, which isn't that bad, right? Because the billions go away and you get 3 over 12, which is just 1/4 or 0.25. So this becomes 1.25. So you basically have 0.021 divided by 1.25, and you get 2.8%. So we now use this value of the base growth rate R to predict the growth rate for 2017. So this becomes our new R. So here's our 2% for the 2017 growth rate. 7.5 billion is the new population because in 2017 that was the population. We still have a carrying, right? A total carrying capacity of 12. And when you do this math, you get 0.011, which is exactly what the growth rate is or was in 2017. So it's reasonable to say that human population has been growing logistically since about 1960. And if population growth continues to follow this logistic pattern, then the growth rate will continue to decline and the population will gradually level out at about 12 billion. That's where the carrying capacity came from. However, human population has not been following logistic growth over longer periods. If we carry this back out, we will see evidence that the population has followed a logistic trend since about 1960. It has not followed this trend over longer periods. Therefore, it's still too soon to conclude whether or not we're on logistic growth, right? There could be all sorts of things that could be happening. So there's what's called the overshoot and collapse phenomenon. This is the phenomenon where a real population increases beyond the carrying capacity in a relatively short period of time and it overshoots, right? And if the overshoot is substantial, then a rapid and severe decrease in the population can occur, a phenomenon known as collapse. This is what I was talking about with like elk and deer, right? If they grow really fast and they outgrow their food source, then large proportions of them will die off, right? And then they'll collapse because they'll collapse back underneath basically their carrying load. And that can be very unhealthy for the animals, which is why they do things like increasing hunting seasons, letting people, increase their limits, reintroducing wolves, things like that to keep the herd from growing too fast and getting above their carrying load. So this brings up all sorts of difficulties of population prediction, because our population will have all sorts of growth spurts and then declines and growth spurts and declines for various reasons, right? So you have a big growth spurt and then wars and all sorts of stuff was happening. People were dying off, right? And then you get a big growth spurt, everything's great, and then a pandemic begins, right? And then people die off until the plague is done with. And then growth spurt, oh, plague comes back. Da-da-da-da, Black Death, right? Everything's happening, horrible times, and then medicine gets better, and then we've been growing, basically systematically since then. So, this example offers an important lesson about mathematical models. They're useful for gaining insight into the processes being modeled. However, mathematical models can be used to predict future changes only when the processes are relatively simple, and human beings are anything but simple. So, for example, it's easy to use mathematical modeling to predict the path of a spaceship because the law of gravity is relatively simple and constant. But the growth of human population is such a complex phenomenon with so many things that can change what can happen that we have little to no hope of ever being able to predict it reliably. So just keep that in mind, that certain things, if things are difficult to understand and difficult to explain, then they're going to be difficult to predict.